Alrighty, lads and ladies, welcome back to Calculus. Today we are going to dive full force into integral calculus. We've had about a full week now of kind of prepping, getting ready, used to concepts and notation. Today I'm going to start writing down integrals and treating them as integrals in full force. We'll also kind of begin to discuss the fundamental theorem of calculus, which will likely spread between today and Wednesday's class. Now, let me go ahead and throw the title card up, and we can get moving. I was not able to, as many of you probably know, I was not able to finish grading the tests on Friday of last week. So I'm going to pick back up with those today and continue moving as quickly as I can through them. I just ask that you be patient with me. If for some reason you have an urgent need to get your grade, totally understand. Just talk to me and same sort of deal. I'll bump you up to the top of the list. So this is MAC2311, section 004, which is Calc 1. And the date today is the 29th, I think. 28th of March, 2022. And what we're doing today is we're talking about this thing called the definite integral, which is section 5.2. And time permitting, we may introduce fundamental theorems of calculus. There's actually two of them. And this is formally section 5.3. All right, so the idea of the definite integral is something that I've thrown out a little bit, but I always made a few simplifying assumptions. Today I'm going to relax those simplifying assumptions, and we'll work strictly in that notation, trying to make sure we fully understand what's going on. So let's do it. Definition. The definite integral of the function f from x equals a to x equals b is the signed area bounded by f and the x-axis on the interval AB. Formally, we write integral a to b like this, as we discussed last time, of f of x dx. And this is, by definition, the limit as n goes to infinity of Rn. And remember what Rn is. That's the right endpoint Riemann sum. So sigma I from 1 to n of f of xi times delta x, where delta x is that ratio b minus a over n, which denotes the length of each subinterval when you chop a b up into n equal length pieces. And xi are the standard right endpoints a plus plus I times delta x. Really, the only difference here compared to what I was talking about on Friday of last week is the underlined word there, signed area. So no longer am I assuming that f is positive. Also, no longer am I assuming that f is continuous. Turns out this can be defined perfectly reasonably well for even discontinuous functions, as long as the discontinuity is not too bad. So if this limit exists and is finite, we call f, note here, if the limit above exists and is finite, then we call f an integrable function. Integrable, kind of meaning what it sounds like, means it can be integrated, right? Where integration is the operation we are performing. So remember, this is the definite integral of the function f of x. So if this thing is well defined, then we say f is integrable, can be integrated, just like differentiable. If f is continuous on the closed interval a, b, then f is definitely integrable finitely many jumps or holes are also okay. So integrable functions certainly are included, or I should say, integrable functions certainly include continuous functions. Every continuous function is integrable, but there are many integrable functions that are not continuous. And sort of the easiest extension I can offer for you here is to say that if a function is piecewise continuous, meaning it's made up of finitely many pieces which are each themselves continuous, then that is guaranteed to be an integrable function as well. Pretty much all of the functions that we mess with are continuous, at least as long as you stay away from certain vertical asymptotes. So pretty much all of the functions we mess with are integrable. If your function does have an infinite discontinuity, a vertical asymptote somewhere between a and b, then that is not an integrable function. So that's just a little mention. And I will teach you in Calc 2, if you take Calc 2 with me, or whomever you take it with, if you take it, we'll teach you how to handle those infinite discontinuities. But of course, there's strange questions there about the area. If your function blows up to infinity, it's possible that area is infinite. We don't want to deal with that right now here in Calc 1. We just want to focus on these nice functions. We call it, say, piecewise continuous functions. Signed area. All right, so that's the relaxation of continuity, right? I don't need my function to be continuous anymore. I don't need my function to be positive anymore either, and that's where the term signed area is coming from. So what I mean by signed area is that area which is beneath the x-axis. So that's the note on continuity, second note here. By signed area, we mean area under the x-axis is measured as being negative. That's all. Okay. Any questions about the terminology or the objects that we're messing with here? These should all be somewhat familiar, but if there's anything here like this symbol or that symbol we want to clarify before I look into examples, now is a good time. Okay. Let's evaluate the integral from 0 to 4 of f of x dx, where f is the function graphed below. Let's say we could do something like let me say something like this. This is 1, 2, 3, and 4. This is the graph y equals f of x. The horizontal is the x-axis. You will see a number of problems like this. And since I have not given you an algebraic definition of this function, right, I haven't given you like a formula for f of x, there's really only one possible way to attack this, and that's by using geometry to find the area there. Now it is important that I tell you that this is the point 3, 1, and that this little arc here is a semicircle. Of course, if this was out of the book or something, you could see clearly from the drawing that this was definitely a semicircle. My art is not perfect, so there's room to question, is that a circle, an ellipse, something else? But I assure you, this is a semicircle. And f is linear from 0 to 2, which means the area bounded by that is a triangle, or, worst case scenario, a trapezoid. So the integral from 0 to 4 of f of x dx, if I give these guys names, maybe I call this area A1 and this area A2, then this would be the area A1 plus the area A2. And each of those we can figure out using some straight geometry. So A1 is the area of this triangle whose base is 2 and whose height, I didn't label that here, the height here is 1. So this is A1 is 1/2 the base, which is 2, times the height, which is 1, because this is a triangle. And A2 is 1/2 the area of a circle of radius 1, right? This is a semicircle of radius 1. So the area of a circle is pi r squared. So this would be 1/2 pi times that radius, which is 1 squared. Thinking here, this is like a triangle. And that A2 is a semicircle. Neither of those is a challenging computation. 1/2 times 2 times 1, that's 1. Plus 1/2 times pi times 1 squared is pi over 2. So 1 plus pi over 2. You can leave it like that. It's absolutely no harm in that. We can try this again, but with a small change. Really, I'm just trying to point out to you the difference between signed area and area. Again, this is a semicircle. This point now is 3, -1. This is 1, 2, 3, and 4 along the x-axis. Very similar. Here's that region A1, and it's identical to the A1 region from the previous problem. Here's the region A2, and it is again a semicircle of radius 1, but now that area lies beneath the x-axis. So when I go to do the calculation here, I'd say that the integral from 0 to 4 of f of x dx, this is A1, this guy has area A2. Instead of being A1 plus A2, this would be A1 minus A2. That area A2 needs to be counted as negative because he's under the x-axis. And this integral, remember, measures the signed area. So again, A1 would be 1/2 times 2 times 1, following the 1/2 base times height rule for triangles. And then we would subtract the area A2, which would be 1/2 pi times 1 squared. So here we get 1 minus pi over 2. This might seem like a really obvious thing, but trust me, there will be some problems where we need to think a little bit carefully about it as we go. Questions on either of these examples here? Okay. I want to begin by sharing some properties of the definite integral with you. These properties will make our life much easier and allow us to begin to sniff out the fundamental theorem of calculus. So I'm going to state this as a theorem. The first couple ones here are by far the most important. Let's let f and g be integral. Then the integral from a to b of f of x plus g of x dx. And anytime you've got an integral with like multiple pieces separated by addition or subtraction, you want to put the whole thing there in parentheses. So this dx, you really need to think of it as distributing over the whole thing. this is going to be the same as the integral from a to b of f of x dx plus the integral from a to b of g of x dx. So the integral plays nice with addition. It also plays nice with subtraction. So if that was a minus, this would be a minus here. The integral from a to b of some constant times f of x dx is the same thing as taking the integral from a to b of f of x dx and then multiplying by that constant on the outside. And this is a rule that we've seen for limits first, then for the derivative, and then for the sigma summation operator. These two things together mean that the integral is a linear operator. Mentioned a few times that linear operators are sort of the ones we like. So the integral a to b is a linear operator. Just like the derivative, just like the limit. It inherits these properties from the sum, from capital sigma, the summation operator, which is also linear. There are other properties though. One useful one is that the integral from a to b of f of x dx is the same as the negative of the integral from b to a of f of x dx. This really comes from the definition of delta x in the Rn expression. If you change a and b, right, delta x is b minus a over n. If you flip those around, then you have a minus b over n, which is the same as negative b minus a over n. We usually think of this as like going from a to b with a very thin strip and adding up all of those areas. If you do that backwards, then you get a negative. That's the idea. There are some other properties that I'm going to share with you today. I'm not sure if we want to drop them in right here. Let me take a quick look at the theorem as it is in the book to make sure I'm not missing anything. Integrability. We'll get there. Oh, sure. Yeah, we can toss those in. Four. If you have a function f and you want to integrate it from a to a, well, then there's no width, right? You can't have any area between some number and that same number. This is always going to be 0. Some of the other ones in here seem a little cheesy to me to list as properties, but I'll play nice. The integral a to b of some constant dx. Well, this means that the area you're bounding is really just a rectangle. So this will be equal to that constant, which is the height, times b minus a, which is the width. There are two other properties I'm going to share with you, but they're really not related to this. Yeah, so we'll save that. This will allow us to attack a lot of stuff if we are able to interpret the function geometrically and calculate the area like that, or if for some other reason we're able to calculate the area associated with each little piece. Let's take a look at an example or two. I saw one up here that looked fun. Let me talk about that later. Let me combine these. Okay. There's a number of ways we could proceed. If you try and think of this whole thing as f of x, though, you're going to have a bit of a rough time. It's not a super nice function. I mean, it's plenty nice, but it's not something whose area we could discern readily using geometry. But if you split it up, as the integral from 0 to 1 of that square root plus the integral from 0 to 1 of 2 minus the integral from 0 to 1 of x, then each of these I can calculate pretty easily using geometry or those properties we discussed. If I let y be the square root of 1 minus x squared, that's the same thing as saying y squared equals 1 minus x squared, which is the same as saying x squared plus y squared equals 1. So this first function here, the function inside my first integral, is what sort of curve? What is this thing? What is this thing?
Ellipse or a circle?
It's a circle. Yeah, it's a circle. It's a circle of radius 1 centered at the origin. Oh, my art is bad today. Now, it's really just the upper semicircle, right? Let me show you in Desmos. Oh, we can do it here. So the upper semicircle is the positive square root. The lower semicircle here, which I'll try to shade in red, this would be y equals negative square root 1 minus x squared. And above here, in purple, is the upper semicircle. If you think about it like starting with x squared plus y squared equals 1 and solving for y squared, you would get this. And then when you take square roots on both sides, you get a plus and a minus right here. So I'm not interested in the red. My curve is just the positive square root. And since it's a circle of radius 1 centered at the origin, this point here is 1, 0. So the area bounded by the purple curve and the x-axis from 0 to 1 is this. Which is 1/4 the area of a circle of radius 1. So the integral from 0 to 1 of the square root of 1 minus x squared dx is 1/4 pi times the radius of that circle, which is 1 squared. So this is pi over 4. So I'm going to do these integrals one at a time.
Excuse me.
Yes.
Can you tell me again why you only use a quarter of it?
I
mean, just I get the negative part, just the top.
So I'm integrating from 0 to 1. So I don't want anything to the left of 0. I'm looking for the area bounded by this curve just from 0 to 1.
Oh, I see.
And because, yeah, we've got the positive square root here, not the negative square root, I'm looking at the 0 to 1 portion from the upper semicircle.
Thank you.
Next up, the integral from 0 to 1 of 2 dx 2 is a constant. So according to that property of the definite integral, this is just c, which is 2 times b minus a, which is 1 minus 0, which is 2. And this was coming from property, what did we call it down here? Property 5. You could, of course, draw the graph of the constant function 2 also, right? And just find the area of that rectangle. Finally, to get the integral from 0 to 1 of x dx, I'll think again about the graph. Y equals x, we know it's just this line with slope 1 going through the origin. So if 1 is right here, then I have just this area to contend with. And that's another triangle, right? So you kind of notice a pattern. The problems like this that we can solve right now are all kind of boring in that they all reduce to some very simple geometry. So this is going to be 1/2 base times height. The curve is y equals x. So the point here is 1, 1. So the base is 1, the height is 1. So this is 1/2 times 1 times 1, which is just 1/2 by the area of a triangle. Right, that 1/2 base times height rule. So I've got all 3 pieces. We can say, therefore, the integral I want, integral 0 to 1 of radical 1 minus x squared plus 2 minus x dx is, like we said before, integral 0 to 1 radical 1 minus x squared dx plus integral 0 to 1 of 2 dx minus integral 0 to 1 of x dx, which was pi over 4 plus 2 minus 1/2. And that's the same as pi over 4 plus 3/2. Nothing too crazy, but it does require splitting up and using the properties of the definite integral and knowing some graphs. Questions on any of these bits? Okay, let's see if we can find something a little bit harder. We've done plenty of approximations. Comparison properties, we'll come back to that. No, I'm not gonna fuck with that. Point, blah, blah, blah. Yeah, a lot of this is the same sort of stuff. Nothing super exciting here. Yeah, honestly, nothing too fresh here until we get down to the FTC, interpreting in terms of areas. This is basically the same thing we just did. Let's try something a little more challenging. Maybe like number 40 there is fun. And then we're gonna move on. We're integrating from where to where here? 0 to 1. Okay. The thing that makes this challenging, of course, is the absolute value, right? If this was just 2x minus 1, rather than the absolute value of 2x minus 1, I could split it up and apply geometry to each little piece. I want to contrast (0 to 1) of 2x minus 1 without the absolute values is definitely not the same as the integral from 0 to 1 of the absolute value of 2x minus 1. So I will go ahead and compute the integral without absolute values first, just to give us the ability to see the difference. Here I can draw the graph y equals 2x minus 1. That's a line with slope 2 and y-intercept -1. So when is he equal to 0? He's equal to 0 when x is 1/2. And by the time it's 1, and by the time we get to 1, we're up here at 2. So the integral without the absolute values is going to be measuring this area down here as negative, and this area up here as positive. So if I adopt that same sort of convention, call this A1 and call this A2, then the integral from 0 to 1 of 2x minus 1 dx without the absolute values would be negative A1 plus A2. And each of those are triangles, boring, boring, blah, blah. So this is going to be negative 1/2 base here, which is also 1/2 times the height here, which is 1, plus A2 is base 1/2 height 1 as well. So this is 1/2 base height. So we get negative 1/4 from the first guy and positive 1/4 from the second guy. This is 0. And my art isn't perfect here, but these areas are the same size. One just happens to live beneath the x-axis, the other lives above. If you look at this guy, which is the one we want, the graph of the absolute value of 2x minus 1 is different. There's a few ways to do this. If you remember your transformations from pre-calculus, you can force factor a 2 inside, and you get 2 parentheses x minus 1/2. And then by the rules for absolute values, this is just 2 times the absolute value of x minus 1/2. And this fella is the normal absolute value function just shifted to the right by 1/2 units. In other words, it's going to take this negative piece and flip it up. We'll call this 1/2. We'll call this 1. We take the regular absolute value graph, kind of stretch it vertically by a factor of 2 and shift it to the right by 1/2 units. we will get this guy, which is the guy we're after. So the area I'm looking for here is this area plus this area. And there is some symmetry we can exploit here if we wanted to. This area is definitely the same as this area. But I'll just follow the same sort of convention. So the integral from 0 to 1 of the absolute value of 2x minus 1 dx, this would be a1 plus a2. Each of those is a triangle, base 1/2, height 1. Right? If you plug in 0 here, then you get height 1. If you plug in 1 over here, you also get height 1. So this is 1/2 times the base, which is 1/2, times the height, which is 1, plus 1/2 times the base, which is 1/2, times the height, which is 1. You get 1/4 plus 1/4, which is not 0, it is positive 1/2. So taking an absolute value inside the integral definitely changes things. If your function is positive everywhere, then it won't change anything, because the absolute value of something positive is just that thing. But if your function is sometimes positive and sometimes negative, then taking the absolute value inside the integral will surely change things. Questions on this example? Okay. There's one other really useful property for estimating integrals. Besides Riemann sums, right? Riemann sums are the main tool for estimating integrals, but there are some slightly lazier ways to estimate integrals. So this is an estimation theorem for definite integrals. And what it says is this: if f of x has absolute min little m and absolute max big M on the interval a to b, then little m times b minus a is the smallest possible value of the integral from a to b of f of x dx. And the largest possible value of that integral is big M times b minus a. The proof for this is best expressed in a picture. I will prove this really quickly. Take your favorite curve, maybe something looking like this. Suppose that maybe B is here and A is here. So the integral is measuring it's enough now, right? This pencil shaded area. And recall that if you have a continuous function on a closed bounded interval, it's guaranteed to attain a min or a max. All right, sorry, both an absolute min and an absolute max. The absolute min is occurring right here. And the absolute max is occurring right here. So let me think about the following areas. Here's the line y equals capital M from the absolute max. And maybe in blue, here's the line y equals little m from the absolute min. I think we would all agree that the blue area down here is necessarily smaller than the pencil area, right? Because it fits inside the pencil area. And the purple area is necessarily larger than the pencil area because the pencil area fits inside of it. So normally the way we would say this is by inclusion. We have the following relationship. The blue area is smallest of the three. The pencil area sits in the middle, and the purple area contains both of them, so he is the largest. But the blue area is little m, right? This little height times the width, b minus a. The pencil area is the integral from a to b of f of x dx. And the purple area is again a rectangle, big M times height, which is the height times the width, which is b minus a. That's it. That's the proof. More shaded boxes. Okay, too much. That's the proof. I've heard this called the world's dumbest integral estimate because it is kind of a silly estimation tool, but there can be some fun problems built around it. So we can take a look at one of those before we start talking about the fundamental theorem. Let's see if we can find a fun one. Estimate, yeah, okay. So number 60 looks like fun. Let's try number 60. the integral from 0 to 3 of 1 over x plus 4. I think it is a good idea to look at the graph of this thing. Everywhere in section 5.2, you want to look at graphs and make sure you're interpreting the integral and areas correctly. So let's begin with that. I look at y equals 1 over x plus 4. I know this is the same as 1 over x, just shifted to the left 4 units. So we'll call this over here -4. And then 1 over x shifted like that looks like this. And we do have a horizontal asymptote y equals 0 that we're approaching, but this is good. So I'm looking for the area from 0 to 3. 3 would be right about here in this picture. So that area I'm hunting for is this area. And if I want to use that estimation theorem, the thing the book calls property 8, we need to find the absolute min and absolute max for f of x equals 1 over x plus 4 on the interval 0 to 3. And yes, you could do this using the closed interval method, but my God, is it more work than you should use and than should be required. Everywhere from -4 to infinity, this is a decreasing function. We're always going downhill over here, right? So the absolute max on 0 to 3 is going to be right here at 0. And the absolute min on 0 to 3 is going to be right here at 3. So the absolute min occurs at x equals 3. And the min value is f of 3, which is 1 over 3 plus 4, which is 1/7. So that's my little m. The absolute max occurs at x equals 0, right? The tallest this function ever is on the interval 0 to 3 is at 0. And the max value is f of 0, which is 1 over 0 plus 4, which is 1/4. So that's our capital M. Now, A is 0, B is 3. So therefore, by the estimation theorem, and the book calls property 8, little m times b minus a is less than or equal to the integral from a to b of f of x dx. It's less than or equal to capital M times b minus a. Little m here is 1/7. So 1/7 times 3 minus 0 is less than or equal to the integral from 0 to 3 of 1 over x plus 4 dx is less than or equal to big M is 1/4. And b minus a is again 3 minus 0. So the lower bound for this integral is 3/7. And the upper bound for this integral is 3/4. So the true value for this integral lies somewhere between 3/7 and 3/4. In actual fact, I think this is like the natural log of 2. And I'll be able to show that to you eventually, but for now I want to make sure we're comfy with this style of logic. Questions on any of the steps here? Okay. I'm going to change tack a little bit now. We're going to start introducing the fundamental theorems of calculus. We did a little bit of this the other day. I would like to explore that a tidbit more. And I think maybe the thing to do is to go ahead and give you the theorem and then try to convince you that it's true. A little preliminary. Recall, we say big F is an antiderivative for little f, provided big F primed is equal to little f. I mentioned this last time, and later in the week, we are going to have a whole section dedicated to finding antiderivatives, and a good chunk of the course from here on out is going to be about calculating antiderivatives. I just want to remind you this definition. And then here comes the theorem. FTC is split into two parts. So there's FTC1, Fundamental Theorem of Calculus, Part 1. And this says if g of x is defined to be the definite integral from a up to x of, I don't want to reuse the variable x here, so f of t gt, then g primed of x is just little f evaluated at x. And I think the place people get into trouble here is just understanding sort of the variables. I'll show you some examples. FTC1 problems are generally very simple until you try to involve the chain rule. I'll show you some examples of that as well. Let me also give you FTC2. FTC2 is the one we use a lot more, especially moving into Calc 2. It is the primary tool we use to evaluate definite integrals. This says if little f is integrable and big F primed is little f, in other words, big F is an antiderivative, any antiderivative for little f the integral from a to b of little f of x dx is equal to big F of b minus big F of a. And because the way we often go about solving these problems is by first finding an antiderivative and then worrying about subtracting it at those endpoints, there is a special notation. This bracket, big F with a to b on the right, is just a shorthand for this. So it says plug this thing in here, then subtract what you get when you plug this thing in here. These are the two fundamental theorems of calculus. There is a little hypothesis built into FTC1, which I didn't mention, and that is if F is continuous, then G is automatically differentiable. That's kind of a big deal, but I want to just get you comfortable with the utility of these things before pestering you with the details. So these are the broad statements. The big deal, of course, is that this relates the operation of take derivative with the operation of find the area. So integrals and derivatives are in some very meaningful sense opposites of one another. And there will be a notation revolving on this thing called an indefinite integral that tries to make that more concrete. Now let me just give you a few quick examples of how we can use FTC1. Suppose g of x is defined to be the integral from 0 to x. So here's your variable, 0 to x, of e to the negative t squared dt. Find g prime. This is kind of blindingly simple. By FTC1, g primed of x is what you get, right? What is it supposed to be? It's supposed to be little f of x, where little f of t is the thing inside the integral. So little f of t is here. It's e to the negative t squared. All you do is plug this thing in there. Integral goes away. That's it. That's the whole problem. There will be one of these on the test. Don't miss it. It's not hard. If I define a function to be the integral from some constant up to x of some other function of t, dt, then to take the derivative of this thing, you just plug this variable down in here. Ridiculously simple, I know. We can write it slightly differently. I could say, calculate d dx of the integral from 1 to x of something like the cosine of the square root of t dt. And then the trick here is, again, just to parse this in terms of FTC1. So I could say, well, let g of x be the integral from 1 to x of cos square root t dt. So d dx of the integral from 1 to x of cos square root t, the thing I was asked to calculate, is d dx of g, which would be g primed. Well, then by FTC1, This is equal to little f, the function inside the integral here, with this t replaced by x. Let's try one nice simple example with FTC2, and then I will let you guys go. Your homework this week is going to largely revolve around the fundamental theorems, but also using those properties of definite integrals. Next time, I will look more deeply at FTC1 and FTC2. I'll give a little bit of a proof for each. But right now, I'm just trying to acquaint you with the notation and the ideas here. Let's evaluate the integral from, let's say, negative pi over 2 to positive pi over 2 of cosine of x dx. This is something that we could not do without FTC2. We could set up a Riemann sum for it, but actually evaluating the limit of that Riemann sum would be very, very hard. So here we're going to use FTC part 2. My little f of x here is cosine of x. This has antiderivative big F equals what? What function can I differentiate to get cosine?
Sine.
Yeah, don't overthink it. Sine x, right? So big F here would be sine of x. Thus, the integral from negative pi over 2 to positive pi over 2 of cos x dx would be that antiderivative sine x evaluated between negative pi over 2 and positive pi over 2. And the advantage of this bracket notation is that it kind of encourages you to break it down into steps. Like, okay, first, find the antiderivative for this function. Okay, then you know that your integral is that evaluated between these bounds. Then as a separate step, go ahead and plug in the bounds. And it's always the upper bound plugged in minus the lower bound plugged in. So this is the sine pi over 2 minus the sine of negative pi over 2. The sine of pi over 2 is positive 1. Minus is this minus. The sine of negative pi over 2 is negative 1. So this is 1 minus negative 1, which is 2. And of course, we can interpret this in terms of areas as well. The cosine function looks like this. Negative pi over 2 happens to be right here. Positive pi over 2 happens to be right here. So we just found the area of this region right here. So I've tried to allude to this. Getting comfy with the fundamental theorems of calculus is mostly about getting comfortable with the notation. In your homework set this week, I'm going to give you a bunch of problems where you use geometry to estimate integrals, or not estimate, but I should say evaluate integrals, looking at the graph. Sometimes the graph will be given to you. Sometimes you need to use your knowledge to come up with the graph. But then you'll evaluate those integrals by calculating the exact area using formulas from geometry, like the area of a triangle, area of a rectangle, area of a circle. The next part of the homework is going to be dealing with functions like this, where your function is defined as the integral of some other function, but rather than from a to b, going from a up to x. So just playing with these sort of functions for a little bit and getting comfortable with what these are, not how to necessarily evaluate any integrals or derivatives, but just understanding what it means to have your variable be the upper bound of integration here. Instead of going from a to b, you go from a to x. The biggest trick to understanding FTC1 is understanding this thing. What does it mean to have your upper limit of integration be a variable? And then the last part of your homework is going to be direct applications of FTC1 and FTC2, some of which will be very much like this. Others will have something to do with physics, and we will talk on Wednesday and then more on Friday about the applications to physics when we discuss something called the net change theorem, which is associated with section 5.4. The other thing that, of course, we're going to need to do is get good at finding antiderivatives, and that's going to be a long-term goal, not a short-term goal. But there are a set of very simple formulas, and I want to give you the first few of those right now. So a few antiderivative formulas. Or formulae is the proper plural. Each thing I'm about to give you here is just reading one of the differentiation rules we know backwards. So for example, you know that if you want to differentiate a power function, something like x to the n, you bring the power down and reduce the power by 1. Well, if you want to anti-differentiate a power function, you need to do the reverse of the power rule, which would mean add 1 to the power and then divide by that new power. Probably the most important single antiderivative recipe, but there are many, many others. I should say this is for all n except -1. If n is equal to -1, then you're looking at the function x to the -1, which is 1 over x. Who has 1 over x as his derivative? Or what would be an antiderivative for 1 over x? What function, when I take its derivative, gives me 1 over x?
ln?
Yeah, the natural log of x. Now, it turns out that whether x is positive or negative, this will still work. You just need an absolute value inside the natural log. Of course, cosine we discussed. Little f is cos x, and antiderivative for cos x is sine x. If little f is sine x, we have to think a little bit more carefully. Who would differentiate to sine x? Well, not cos x. The derivative of cos x is negative sine x. So the guy who would differentiate to positive sine x is negative cos x. Some other results from trig. Secant squared, you know, is the derivative of tangent. So an antiderivative for secant squared is tangent. And secant tangent would have antiderivative secant. Also the inverse trig functions, right? Which you know, there's a corresponding antiderivative for every derivative, you know. I'll leave it at this for now. This is more than enough to give you in one day. But we will expand on this, and you can find two different places where this a more full list is offered. One of them should be in section 4.9 here. No. Well, maybe not. Maybe they save it for 5.4. All right, that's fine. Then we'll save it for 5.4 as well. All right. So we'll start with these. We will build on this, of course, and just be aware that every derivative you know is really also telling you an antiderivative. You just read the thing backwards. Next time, we're going to go deeper into the fundamental theorems. We'll offer a little bit of a proof, talk about functions where the variable is the upper bound of integration, and get ready to talk about some cool applications to physics. Any burning questions for me before I let you guys go for the day? Alrighty, then I'll go ahead and end the meeting here. Have a good rest of your day. I'm going to go ahead and pop open your homework in the next few seconds. Work on at least some of those problems before class on Wednesday, and I will see you guys then. Take care.